This conference will now be recorded.
So good afternoon, students. Today we are continuing discussions on waves, and we'll be discussing few important things, like we'll try to understand how wave propagates through elastic medium, through air, through crystalline solids, etc. And for that we'll take up a spring model which will help us to understand how waves or disturbance propagates through elastic medium. Then we'll see, depending on the relation between the velocity of the particle or direction of velocity of the particle and the direction of propagation of the wave. Waves are classified again into two. Those are transverse and longitudinal wave, and we'll take up few demonstrations and try to understand which one is transverse wave, which one is longitudinal wave. And then we'll learn few important definitions today, which are very important to discuss the wave equations and to solve various problems, etc. Excuse me, it got muted, so I'm back. So let us start our discussions. Before we discuss today's topic, I'll just recap shortly what we have discussed already yesterday. So yesterday we have discussed what is called wave and what is wave propagation or wave motion. So wave is a kind of disturbance, as we have seen. It is kind of a disturbance. Actually, there is a nice example. If you see wave or disturbance, see when in a cricket gallery, people cheer up the players, then they move in a particular direction. Suppose there is a big crowd, so all of them move some direction together, like some group of people move in that direction, then other group moves, then the next group moves in a particular direction. Okay, this is how a disturbance propagates. So this is also an example of how wave propagates. Now we have learned what is wave, and today we'll see how it propagates from one point to another through the medium. And we had discussed also with the example of water wave. So circular waves are produced, like these are crests and troughs, or water particles moves ups and downs, and that's how wave propagates like this, as a sinusoidal wave. Okay, so we have seen that the medium through which the disturbance propagates, that medium as a whole does not flow, does not propagate. It does not propagate. they just oscillate. The particle of the medium just oscillate about their mean position, sitting over there. Like say water particle, which are here, they will move in this direction. The water particle here, they will move in this direction, but they are not going this way. Neither this is going this way. So the medium as a whole does not propagate, but the disturbance propagates through the oscillation or vibration of the medium particle, okay, or material particle. So that is what I wanted to see. Now we'll see how wave propagates practically in elastic medium through an example or through a demonstration, which is called spring model of propagation of waves. So we know an elastic spring, when it is actually applied some force at one end, whereas the other end is fixed with some rigid support. Actually, when it is having a normal length, suppose it is L, this is the normal length, then it does not have any oscillation, or there will be no net force. Okay, no net force. But when the spring is stretched by applying certain force here, by applying certain force, if the spring is stretched, let us look like this. Okay, when it is stretched, then what happens? Because of this elastic property, the spring will actually exert a force against this force. Suppose this is the force applied to stretch the spring. So suppose this is the change in the length. This is the equilibrium position. Okay, this was at equilibrium position. Now it is actually stretched by some length x. So there will be a force acting in the spring in the opposite direction to the displacement or to the applied force. Okay, so this, what is the role of this force which is acting opposite to the displacement, in the direction opposite to the displacement? So this force actually called restoring force. It means the force which will restore the length of the spring to its normal length. Suppose it was L, now it is L plus X. So this force, restoring force, let us say this is small f. This restoring force which is acting against or acting in a direction opposite to the displacement will try to bring the spring to its normal length or restore its original length. Not only length, shape, size, whatever it is. In any elastic case, this restoring force is there. Not only stretching, when you compress, suppose this is the normal length. Now if you compress it, this we have certain experience, we have some experience with this, I hope. If you compress a spring and leave it, suddenly it will jump up, right? So if you apply certain force to compress the length by some x, then the spring will actually give a restoring force against this applied force. So this restoring force, again, see the displacement is happening in this way, restoring force is in the opposite direction to the displacement, direction of displacement. So this force actually will help the elastic medium or elastic object to bring its original shape, size, to bring it to its original shape and size. So this is restoring force, and that acts in any inelastic medium, especially for spring. We will be able to understand very easily. That's why you have taken spring. So there is a collection of spring, 1 2 3. Suppose the one end one end of this spring is attached to a rigid support, the other end is connected to spring 2, and the spring 2 is connected to the spring 1, and one end of the spring 1 is left bare. Okay, it is not, it is actually free. Why free? To apply force on it. So it is seen, if you stretch this spring, then since this spring is also connected to the spring 1, suppose you stretch the spring past spring 1, there will be a restoring force. Suppose it is stretching, so restoring force will be in this way, right? Since this spring is connected to the other one 2, and 2 is connected to 3, if you stretch this spring, you'll see that stretch will be actually happening for spring 2 and 3 also. That means the disturbance you have given, see, originally length was L, now you have stretched it. That means you have disturbed the length, original length of the spring. And since this spring is connected to this spring, so this also will get disturbed. So this also will get disturbed. That means it also will get stretched. Similarly, this also will get disturbed according to elastic property, because they are connected to each other also. So that's why all of them will be disturbed. Okay, now if suppose you stretch it and then suddenly leave, suppose you apply certain force F, so it will get stretched, this also will get stretched, and also this will get stretched. Now if you suddenly leave this force, you just withdraw this force, that means you are suddenly leaving it. So what will happen, it will get compressed, because the restoring force will try to bring its bring the spring to its original length. Okay, so that's how it will get compressed. Okay, it will get compressed. Because of this compression, this also will get compression, other one also will get compression. That means, since these springs are, this is a collection of springs which are attached to each other elastically, they are attached to each other. So whatever changes you do, or whatever stretch or strain, stretch or compression you make with the first spring, the same disturbance will be seen in this. And in fact, when this is getting stretched, after that this will get stretched. Okay, slowly. That means the disturbance actually propagates to this and to this. In case of compression also, after this gets compressed, this will be compressed. After this gets compressed, this one will again get compressed, and they will have some time lag. This is called phase difference. So they will have some time delay. I mean to say, if you stretch this one, immediately it will not get stretched. After it gets stretched up to its elastic limit, then this will get stretched. Similarly, with this spring 2 also, when this gets stretched maximum up to its elastic limit, then this one gets stretched again. So the disturbance stretch or compression both are actually propagating from one end to the other end of the series of the spring. I hope it is understandable. When you leave it suddenly, this stretch spring will get compressed first, then the second one get compressed slowly, the third one also will get compressed. So this is how you will see the stretch or compression throughout the spring actually. Here, then it will come to here, then it will come to here. So this is how wave propagates. That means in a water, when the wave generated and it propagates, then first the adjacent layer of the liquid will get disturbed, and that disturbance will be actually transferred to the next layer of the water, then that will transfer to the another next. Okay, this is how the wave propagates in elastic medium. Okay, so through this compression and stretch, we can understand how wave propagates in spring model of spring as a so how spring actually in practical medium, how wave propagates in, so that we have understood now with the spring model. Now similar thing actually, see, so propagation of sound wave through air, how it happens? Propagation of sound waves through air. And propagation of sound in solid. These two things we'll discuss. Propagation of through solid. Obviously crystalline solid will say. So when sound propagates in air, what happens? Suppose I have a region of air, okay, like this. A region, suppose in when there is no sound, this is the medium, okay, this is the medium through which the sound propagates, that is the air. This is the air column, suppose, or layer by layer I am just trying to show you the air. So this is the air column. Now when sound wave actually is created, then what happens? The region near to the source of the sound will get uh, they will be actually compressed in the sense the sound wave will actually make the air molecules to get compressed. That means the layer of the air in this region will get compressed. So due to this compression, what will happen? The density rho increases. If this increases, rho increases, then pressure also increases. When the density of the layer in any region increased, then pressure also increases. And you know, force is actually pressure by unit area. So when a region get compressed by sound wave, then the molecule actually they come very close to each other. That's how the density increases. The density of the air increases. When the density of the air increases, then the pressure also will increase. Pressure also will increase. So due to this compression, what happens? The molecules over here, since the density is too high, they will try to go to the rarefied layer where there is a much place to go. So the molecules over here which are compressed together will actually try to move or will move to the other region. When those molecules and all they just move to the other region, there also the compression will happen. And then again the air molecules and all they will try to move to the other side. So when they go there, that layer also get compressed. Okay, so this is how the compression, the disturbance compression is actually moving through the air. Okay, through the air. Now if the density of air molecules somehow decreases, then it is called rarefaction. So compression and rarefaction. When the gas becomes rarer or the density of the region of air molecules or gas molecules in the air decreases, then it is called rarefied. Suppose this region, some region is rarefied. Okay, rarefied. Then compared to other region, when a region is rarefied, so the gas molecules from that region will try to go and make a crowd over here to make it again denser. Okay, so rarefied or compressed. So rarefied, when the gas molecules or air column is rarefied, then the molecule compared to the other region of the air, so the air molecules will come to this side and this will get compressed. Okay, whereas this will get rarefied. So when the gas molecules go from a compressed region to the rarefied region or less dense region, actually they will create they are creating rarefied region in the behind and making a denser region front. Like that, rarefaction and compression both are actually traveling in a particular direction. Okay, some layer is first compressed, and then let me draw. Suppose first this region is compressed, then the molecules will go to this region because they will not prefer to be where the density is too much. So this initially, suppose this was rarefied region, or density was less, but when these particles are or molecules are coming to this region, they will make this region again dense, whereas they will leave the first region as rarefied region. Rarefied region. So you can see the compression, the disturbance compression has moved to here. Okay, and here rarefication happens. Further, the molecules from this region, compressed region, they will prefer to go to the next rarefied region. So this region will get compressed again, whereas they will leave a region which will be again rarefied. Okay, so this is how you can see both the rarefaction and the compression both are actually moving or making a progress throughout the medium of the air. So this is how sound wave propagates in air by compression and rarefaction. Rarefaction, okay? Rarefaction. Rarefaction. Compression and rarefaction. Means density is less, becoming density is less. Rare means less density. Suppose this is density 2, and compression in the region density is 1. So density in the compressed region will be more than the rarefaction region, and hence by boil flow pressure will be more over here in the denser region than the rarefaction or rarefied region. Okay, so this is how the pressure changes point to point, not only a particular region. This compression or rarefaction happens throughout the medium, and thus by compression and rarefaction sound wave propagates in air. Okay, so we have understood how air propagates. It is actually propagating by changing the pressure in the air. Okay, so how sound wave propagates through crystalline solid? We have seen gas. Now we'll see how sound wave propagates through a crystalline medium. Through a crystalline solid. Excuse me, I need to drink some water. Actually, you will be very much surprised to know that a solid is considered, or in a crystalline solid, in a crystalline solid. Crystalline means where the atoms are arranged in a particular periodic manner. Crystalline solid. In a crystalline solid, atoms or molecules of the solid solids are connected by elastic spring. Elastic spring. Actually, this is a model, spring model. You know, like say you have in a solid, you have two atoms. They have bond between them, but this bond will actually act as an elastic spring. That's how it is. It is connected to. So these are the atoms. Similarly, you will get to see some atoms in this way also. Some atom from here again with the spring. Some atom here. Okay, so these are the atoms which are connected to its neighboring atom by an imaginary elastic spring. So at normal pressure and temperature and normal temperature, generally, there will be no change in the length of the spring. If there is no change in the length of the spring at normal equilibrium position, then there will be no vibration or no oscillation. But if sound wave is propagating through the crystalline solid medium, it will actually disturb the length of this of the spin, like it will disturb the spring between two atoms. Okay, and when the length get changed, then there will be a oscillation. There will be an oscillation actually. There will be an oscillation. Similarly, in this case also, as you have seen in the spring model, how it goes, so each atom is at equilibrium state initially. Now, if the sound or the force is applied to the atoms, then actually the atoms will be displaced from their equilibrium position, and thus returning force will be arising. The disturbance produced by the force to the next atom, and so on. So what does that mean? That means suppose this is getting disturbed, so that disturbance will go to here, and that disturbance will come here. So that this is how sound wave will actually propagate through the crystalline medium. So we have assumed that the bonds between two atoms are elastic and just like springs. So when you give some disturbance like sound wave or any acoustic waves, then the springs, they are actually getting disturbance, and hence their length will be changed. Because of that, there will be oscillations. If you stretch or strain, there will be restoring force, and that restoring force will actually make the disturbance transferred to the other spring. This is how the atoms will vibrate. So this is called actually lattice vibration. Lattice vibration you will learn in your higher classes. Lattice vibrations. This is called lattice vibrations. Okay. All right. We'll go to the other part of today's discussion, that is classification of waves. It is actually depending on the direction of velocity of the wave and direction of velocity of the material particle in the medium. So depending on this, the wave can be classified into two categories. One is transverse. Transverse wave, and another one is longitudinal wave. Okay, so transverse wave and longitudinal waves. So what are those? Let us now learn. See, if the wave, first one, if the wave is propagating in this way, okay, but the particles of the medium are vibrating or oscillating in this direction or in this direction, that means perpendicular to the direction of motion of the wave propagation, then this is called transverse wave. I'll just give you an hint. See, suppose this is x-axis. So wave as a whole, the wave is propagating in this direction, but the material particles are, suppose, moving up and down, okay, moving up and down. When this happens, that the material particle are oscillating in the direction perpendicular to the direction of the propagation of wave, then it is called transverse wave. That particular wave is called transverse wave. The waves in which the individual particle of the medium oscillate perpendicular to the direction of the wave propagation, then that is called actually transverse wave. You can get some example, like, see, example is electromagnetic wave is a transverse wave, EM wave. Electromagnetic wave is an example of transverse wave. Okay, that means, you know, in electromagnetic wave, what happens? Generally, wave propagates in this way. Okay. Electric and magnetic field vectors are moving in a direction perpendicular to the direction of propagation. Suppose the B is propagating in this way, and this way means this, suppose this is x-axis, this is y, and this is z. So along the z direction, oh, in fact we can show you here also. So this is, suppose, some this is the total wave, but see, the material particle, I'm sorry, here there will be no material particle. The transverse wave, in case of electromagnetic wave, actually there are electric, time varying or oscillating electric and magnetic field. So electric and magnetic field, their directions are perpendicular to the direction of the propagation, wave propagation vector k. All right. So electromagnetic wave like light, then radio wave, X-ray, gamma ray, these are actually of example of transverse wave. We'll demonstrate what is transverse wave. Longitudinal wave is the waves the waves are called the waves for which the the particles material particles moves in a direction moves in a direction parallel to the direction of wave propagation. To the direction of, so they're parallel to each other, direction of propagation and direction of material particle, direction of propagation of direction of vibration of material particle. Okay, let us see the demonstration, then you will be understanding it again vividly. Suppose there is a string. This is string. Suppose there is a string supported at the rigid. It is actually rigid support. So the string is tied to a rigid support at one end, and the other end is held by this person. If the person somehow give a pulse in the upward direction, a jerk, if it gives a force or a jerk or a pulse, such that there is a kink produced, this is called kink. There is a kink produced or a disturbance produced. Kink, this is a kink which is produced by this man on in the string, and you look, this is actually our practical experience says that this kink will actually move up to the end. So you can see that this kink is what? The kink means, see, the material particle which were here originally, they have moved to here. That means the material particle is moving in the upward direction or maybe in the downward direction, whereas the wave propagates. So this will actually, see, at each point, so kink was here sometime, and then next time it will come here. Okay, come there. So actually the kink is not moving. Actually the disturbance is moving, which is making a kink at each point of the string. Okay. So this is a kink, and this kink will actually move further toward the right, and that's we can say that this is an example of transverse wave. The wave produced in the string is actually a transverse wave. Look, you can look, the wave is propagating in the left to right direction, but material particles are moving up and down. Here also up, here it is down, here it is up, and then here will be some some particles which are moving in the down, whereas your wave is propagating in this way. Sinusoidal wave will be produced if you give a jerk, smart jerk, and then you hold it. Okay, so this is the wave. So I'll write the waves or wave produced in a string is an example example of transverse wave. Transverse Okay, so the wave produced in string is called actually a transverse wave. Now we'll see what is longitudinal wave. We have already written down the definition. If the particles of the medium oscillates in a direction parallel to the direction of the propagation of wave. Then the wave is called longitudinal wave. Okay, that means, if suppose the material particle moves in this way, and this is, and wave propagation also happens in this way, then the waves will be called longitudinal wave. Okay, let us see the demonstration in this case also. See, just to make you understand, a demonstration has been given here with the air enclosed at one end. At one end, gas actually in a cylindrical container which has one end closed, and in the other hand there is a movable piston. This is actually a movable piston. It can go left and right. Now see if this man is actually pushing this piston, so what will happen? So the air molecules which are next to this man will get compressed, and then the density or the pressure will increase. So there will be a change in the pressure between this and this region. So there will be a force, kind of restoring force. So when this is getting compressed, then these compressed molecules or atoms will try to go to the rarefied region, leaving this medium here. Okay, so when these get compressed, the compressed molecules will try to move to the rare region, and thereby that region will again get compressed, or density will increase. So that's how increasing density and decreasing density, that means compression and rarefaction, they actually moves in this direction at the same time, the sound wave will also move in this direction. Okay, so if the man is actually, after compressing all the way up to here, if the man is bringing it back, this piston, if they are just pushing in the opposite direction or towards the left, then the compressed air actually get rarefied compared to the other region, so the pressure will be becoming less in the rarefied region. Therefore, the molecules in the adjacent region, they will actually rush to go to the rarefied region, and thus they will increase the pressure further in that region, and the region from where they are coming, those regions will be becoming rarefied. And this is how rarefaction and compression moves from one place to other, and at the same time the sound wave also will travel through the air. So this is how actually in this case we see both the material particle moves in this direction, and rarefaction and compression also moves in the same direction. Okay, along the same direction. This is what I just wanted to say. So the compression and rarefaction moves in the same direction in the same direction as the air molecules move. Okay, both rarefaction and compression, they are moving in this direction. At the same time, the air molecules are actually trying to move from rarefied region to compressed region to rarefied region, and thereby they increase the density of particular region, and from there, that particular region again gases will go to the rarefied region. So the compression and rarefaction, these are actually moving through the air, and so compression and rarefaction moves in the direction in which direction rarefaction and compression moves, in the direction of propagation, because that is the direction of propagation of wave. Okay, for air. So we can blindly write now that sound is a longitudinal wave. Sorry. Okay, so this is what is the demonstration. So we have seen how wave propagates through material medium. So these are transverse wave, and also we have seen transverse wave and longitudinal wave. In the transverse wave, the material particle oscillates in the direction perpendicular to the direction of propagation of the wave, and in the longitudinal waves, so longitudinal waves are the waves where the metal particle moves in the same direction or travel in the same direction, oscillate in the same direction as that of the direction of propagation of the wave itself. All right, now I'll take another 5 minutes to define few important parameters which will be useful So first parameter is amplitude. Amplitude. What is amplitude? That is the maximum displacement in either direction. Maximum displacement. Maximum displacement suffered by particle suffered by particle by the particles by the particles of the medium about their mean position. I'll give you an example. Mean position. Amplitude is generally denoted by A. Amplitude is generally denoted by capital A or sometimes small a, etc. Okay, so if I have a sinusoidal wave, so suppose I take a sine curve, it is like this. Okay, so displacement means particle can, so displacement at each instant, displacement can be different. So it can be lowest as low as 0, it can be maximum also. In case of sine, the maximum amplitude will be plus or minus some a, plus a, and suppose this is minus a, this is minus a. So this is the maximum displacement in the opposite direction, and this is in the positive direction anyway. So this is one amplitude, this is amplitude. Okay, these are called amplitude. Whereas displacement at each point, see each time displacement, these are the displacement, instantaneous displacement. Instantaneous displacement means at any instant of time displacement is that. If I just write this x of t is equal to a sine of omega t. Okay, so displacement is the maximum, sorry, amplitude is the displacement, maximum displacement. Now we'll go to the time period. Time period means, see in this wave we have one crest, one trough. Crest and trough. So one crest and one trough, this will give you a complete oscillation, or this is a complete wave, complete oscillation, or a full cycle of oscillation. Complete oscillation. All right. So the time it takes, suppose here it is t is equal to 0, but here there is some time. So if it is capital T, when the wave starts from 0 and then it goes to some value, and thus it goes to positive maximum, then from there it starts decreasing, and it will decrease through 0 up to then next in the opposite direction. Okay, and then it will becoming 0. So this is a complete oscillation, and the time it takes to complete a full oscillation, or the time, this is called actually time period. It is the time which a material particle of the medium takes to complete a full oscillation or full vibration. In case of simple harmonic oscillator or simple pendulum, see if it is starting from here, from mean position, it will go to this way, suppose plus, then it will actually come back to the mean position, then it will go to the other side, this position. Okay, so this is how it will continue to move. So the displacement on either side, maximum displacement on either side is called actually amplitude, and to complete a full oscillation, the time this pendulum takes is called the period, time period. Okay, so amplitude is denoted by A, time period, that is the total time taken by a wave to complete a full oscillation, time period. So this is denoted by capital T. Then frequency. So frequency means how many or number of, it is frequency, number of oscillations, per second. Number of oscillations per second is called actually frequency, and frequency is denoted by nu, and time period, they have a relationship this. Sorry. Okay, so this is the relation between frequency and time period. So frequency is 1 over the time period, because we know if one complete cycle is in t second. Okay, in t second. All right. So in t second, and we know the frequency is actually the number of, this is one complete cycle in t seconds, complete oscillation. So t second is taken by the wave to complete a full oscillation. So 1 second is 1 over t, and this 1 over t is equal to nu. Okay, it has unit hertz. Actually, time period has unit second, and amplitude has unit centimeter meter. It has a dimension of length, so it has unit of length. Angular frequency. So what is angular frequency? Angular frequency it is the rate of change of the phase, the rate of change of phase. The rate of change of phase, okay, it's called angular frequency. The rate of change of phase is called the angular frequency. Okay, so angular frequency is denoted by rate of change. So this is 2 pi is the total phase change happens during time period t. So this is actually angular frequency, and this can be written as 1 by 1 over t, so 2 pi nu. Now wavelength is the length or the distance of a full length. So if this is the full length, one crescent length, so this length is called a wavelength. A full length of wave is called a wavelength. Okay, the distance covered by a wave during the time in which a particle of the medium completes a full vibration. So this length, it is actually full vibration, length of the full vibration. This gives the wavelength. Wavelength is this much. Okay, this is the wavelength. It is denoted by lambda and unit will be in angstrom. Okay, so and if we take reciprocal of frequency, okay, wave number is denoted by nu bar. It is actually the number of wave present in a unit distance. That means it is 1 over lambda. Okay, angular wave number. Okay, anyway, so there is a relation k is equal to 2 pi by lambda over here. So angular wave number of propagation. Okay, we'll stop it here for today. Next day we'll try to pick up few numerical problems on these definitions. Okay, with example and all, we'll try to solve few numerical problem and then we'll proceed further in the next class. Okay, so we'll stop it here for today. Bye for your patience.